So we were just saying when my battery died that we found the mole to mole ratio from the balance equation to be 1 to 2, 1 mole of lead nitrate to 2 moles of potassium iodide. Now Zach's going to tell us how we find the mole to mole ratio that we actually used in this experiment.
So we took 3.08, and since there's 1 mole, you divide it by 3.08 again, so you get 1 mole of PB, or not PB, I'm sorry, potassium nitrate.
No, lead nitrate.
Excuse me?
Lead nitrate.
Lead nitrate. I gotta get these down. And that's 1, and that equals 1 mole. And then you take 3.08 times 10 to the negative third, and you divide it by 0.187, and you get 6.07 mole of potassium iodide.
Good. Okay, so remember when we did this problem in class, I think it was practice problem number 9, where we found the number of moles and then we needed to get a mole ratio, so we divided through by the smallest number. Well, 3.08 times 10 to the third is the smallest number. It's smaller than this number. So if we divide it by itself, we get 1. If we divide 0.0187, the number of moles of potassium iodide by it, then we get 6.07. So divide through by that smallest number to find your mole ratio. So instead of a 1 to 2 ratio that we need from the balance equation, we actually have a 1 to pretty much 6 ratio. So how do we figure out which one's the limiting reactant if we need a 1 to 2 ratio, but we have a 1 to 6 ratio? So what's our limiting reactant, Zach?
Potassium, or
Lead.
not potassium. I keep missing
The P is bad.
I know. Lead nitrate.
Okay, so how do we know? Well, we have, if we need 1 mole of lead nitrate for every 2 moles of potassium iodide, and we have 1 mole of lead nitrate for every 6 moles of potassium iodide, then clearly we don't have enough. We would really need like 3 moles of lead nitrate for 6 moles of potassium iodide. So we don't have enough of the lead nitrate. We have extra. Instead of 2 moles, we have 6 moles of the potassium iodide, so that's plenty. We don't have enough of the lead nitrate to go around and react with all of that. So our limiting reactant is lead nitrate. So why does it matter which one's the limiting reactant? Well, in our next step, when we choose which one to use, we need to choose to do our math based on the limiting reactant, because the limiting reactant is the one that's going to get used up and make the reaction stop. Right? We could continue to just add and add and add this potassium iodide, but no more reaction would happen because we already have an excess of it. We have plenty of it. Okay, we're going to run out of the lead nitrate here, so we need to do all of our math based on lead nitrate because we run out of it first. It stops the reaction. So, Zach, number 11 says here, using the limiting reactant in the experiment in the balanced chemical equation, how many moles of that precipitate, lead iodide, what do we expect to make? All right, so we know how many moles of our limiting reactant we started with. How many moles of the product can we make using it?
1.
Well, it's a 1-to-1 ratio. So we know that for every mole of the lead nitrate, the limiting reactant, we're going to make 1 mole of the lead iodide. But how many moles of the lead nitrate did we actually have? Eek, I'm filming my finger.
3.08 times 10 to the negative third.
Yes. So if we have, and we're going to write it down here, 3.08 times 10 to the negative third moles of lead nitrate. Moles of lead nitrate, because I'm the meanest person ever about units. It's not moles of kittens. Kittens are the only unit that doesn't have to be written. Okay, so where are we? Moles of lead nitrate. Oh, that's lead iodide. We need lead nitrate.
Oh.
It'll be so much easier. Like 2 modules from now, you guys will learn all of these ions, like nitrate and phosphate and all that, and then it'll be so much easier for you to do this. You haven't learned this stuff quite yet, so it's much harder. Okay, so now we're going to convert moles of lead nitrate to moles of lead iodide. So multiply by the mole to mole ratio, which luckily is 1-to-1. So put a multiplication sign. Oops, catch the pencil.
Times.
Okay, so now what do we want to change to? We want to end up with moles of lead iodide. We want to cancel out moles of lead nitrate. So we're going to have moles of lead iodide in the numerator, moles of lead nitrate in the denominator.
So,
Well, I'm not helpful at all over here. Here. So remember, when you want to cancel something out, you're going to do moles of what you want, which is lead iodide, and you're going to cancel out moles of what you want to get rid of, which is moles of lead nitrate. So see how this will cancel
okay.
with the denominator? So how many moles of lead iodide react with moles of lead nitrate?
1.
1 to 1.
1.
So 1 mole of that, 1 mole of that. So basically we're not changing the number at all, we're just changing the units by doing this.
Okay.
So now we end up with moles of,
3.08.
yeah, and I actually put PI2 instead of PBI2, so can you put a B in there for me? We don't want any phosphorus in this experiment. All right, so moles of lead iodide. So we didn't change the number, we just changed the units, but we have to change the units to find out. So basically what this is saying is that for every 3.08 times 10 to the negative third moles of lead nitrate we reacted, we get 3.08 times 10 to the negative third moles of lead iodide. Well, what does that matter? Well, that tells us how many grams we should have made if we use this molar mass, which Zach has nicely written in the edge here. Remember on the last page we found that the molar mass of lead iodide was 461.0 grams. So we're going to use that molar mass to convert the number of moles that we have of lead iodide to grams of lead iodide. So, and I told you guys the answer earlier so that you can erase the answer so we can actually find it. I told you all the answers so that you could try it at home and see if you got to the right answer in the end, but now we're going to show you how to get it. So Zach, go ahead and convert moles of lead iodide to grams of lead iodide using your molar mass.
Oh.
So write down your what you know, moles of lead iodide. So 3.08 times 10 to the negative third moles of lead iodide. And then multiply it by the molar mass. Okay, so Zach's taken our moles of lead iodide, converted, canceling the moles of lead iodide, leaving us with grams of lead iodide. He found that we produce 1.42 grams of lead iodide in this reaction. So what we did is we made that reaction, we found that yellow precipitate, we filtered it out through the filter paper, we dried out the filter paper maybe in an oven or maybe by letting it sit out and let that water evaporate out, and now we've got 1.42 grams of lead iodide. Yeah, well, we did that.
Oh.
Now we did it for everybody. So if we got 1.42 grams of lead iodide, how does it compare to the grams of lead iodide that we recovered and dried in the oven? So what we found here is that we should have produced 1.42 grams of lead iodide if this reaction went perfectly. Now on the other page, we found here, when we subtracted out the mass of the filter paper, we found that, hi, we're shooting a video, how are you?
Oh.
Peter's here.
Hello.
We found that we have 1.45 grams of lead iodide, and so if we produce 1.45 grams, wait a minute, Peter, I'll talk to you in a second, and we actually found that we have 1.42 grams, then is that pretty close, Zach?
Mm-hmm.
Okay, it's very close. And what could cause that 0.03 gram, which is a very small error?
Table could have moved and shook some of it off. Someone could have like breathed on it or something and moved.
Okay, contamination is very likely. 0.03 grams of some dust falling in or some kind of contamination, very likely. Or it could be that we didn't dry all the water out, so that the extra 0.03 grams is just water that we didn't dry out. So that's how you do this experiment, and we'll be back later.